Hello, this is Mrs. Hilt with today's lecture on work. Please follow along with the student notes that are posted on Google Classroom. There are a couple things that you guys will need to fill in, and it'll be much easier to do with that. You can also do it on a separate sheet of paper if that's not an option. And you will also need a calculator for later in the lecture. Okay, first activity. Am I doing work? All right, so we got a list of activities here, and I want you guys to read through them and identify if you think that you would be doing work in these. You'll fill in your either yes for work or no for not working in this table. The right-hand side, the physics definition, leave blank for now. We will come back to that later on. So pause the video and press play when you're ready. Okay, so what is work? Well, the Merriam-Webster definition of work is an activity in which one exerts strength just to perform a physical task, a mental task, or mental effort, any type of labor, task, duty. And some of that actually does work with the physics definition, but the physics one is more specific, and it is work is the force used to move an object. So two things must happen in order for work to happen. So the force must be applied and an object must move. It also has to happen in the same direction. If those two things don't happen, or if they happen but not in the same direction, then work is not done. Now, how will we calculate this? Force is applied to an object multiplied by the resulting displacement. So calculating work is the force times the distance or the displacement. And the units for force and distance are going to remain exactly the same, newtons for force and distance for meters. You're probably wondering why there is this thing called joule for work, but that is because a joule is a newton meter. And all of the units that are listed below the joule are all of the units that make up a newton with an extra meter in there. So that's why a joule is a newton meter. And when you guys are performing these calculations and reading the problems, this is a criteria that must be met. So force must be applied to an object. Distance must have, there must be something. The object had to have moved. And if you were to plug a 0 into the equation for each of those, or either of those, you'd also get a 0 for work. And they both also have to happen in the same direction. And we'll go through more examples of that one later. So something that might be a little bit of a surprise is that work is a scalar quantity. But when you think about how you calculate work, it makes sense because you're multiplying two vectors together and they essentially cancel out their vectorness, making a scalar quantity. Work does have the same signs as force because force is used to calculate it. So if you have a negative force, your work is going to be negative. If you have a positive force, your work is going to be positive. And it all goes with the same directions that we're used to. So west, south, left, down, all negatives, and east, north, right, and up are all positive directions. Oops, that was supposed to be over the plus. All right, let's go through some examples for you guys. So first one, a boy lifts a bucket of water vertically. Does he do work on the bucket? I want you to pause the video and answer the questions. When you're ready for the answers, press play. All right, is there a force on the bucket? Yes, in the upward direction. Does the bucket move? Yep, he picked it up, moved vertically. Is the force and displacement in the same direction? Yes, again, both up. Therefore, yes, he does work. All right, I hope that one went okay. If it didn't, don't worry, we got 3 more. All right, example 2, a boy holds a bucket of water. Does he do work on the bucket? Pause the video, answer the questions, press play when you're ready. All right, is there a force on the bucket? Yep, that's what's holding it. Does the bucket move? No, it stays in place. So that means that the force and displacement cannot be in the same direction if there is no displacement. If there's no displacement, no movement, there is no work. Example 3. The boy holds a bucket of water and carries it horizontally. Does he do work on the bucket? Pause the video, answer the questions, press play when you're ready. Okay, is there a force on the bucket? Yes, and my purple and red arrows switched, I guess. There we go. The bucket does move to the right, and the arrows are color-coded, so the up is, yeah, purple. Is the force and displacement in the same direction? No, they are perpendicular. And because they are not in the same direction, there is not work done on the bucket. Okay, they have to be in the same direction, otherwise there's no work. All right, last one. The boy pushes a bucket of water horizontally across the floor. Does he do work on the bucket? Pause the video, answer the questions, press play when you're ready. All right, is there a force on the bucket? Yes, to the right. Does the bucket move? Yes, to the right. Is the force and displacement in the same direction? Yes, both to the right. And yes, we do have work. Same direction, therefore there is work. All right, now let's go back to all of these activities. And after hearing that to have work, you need to have a force and a displacement in the same direction, or a force has to be applied and the object has to move in the direction that the force was applied. I want you to go through and answer either yes or no for the physics definition. And I want you to explain why. It doesn't have to be long sentences, but just a short explanation. Press play when you are ready. All right. Does the student do work on the wall? No, the wall does not move, therefore there is no displacement. Next one, yes, the force applied to move the chair. The chair moved and force was applied. It did not say if it was in the same direction, but we would have to assume that if you push a chair that it moves in the direction that you pushed it. Lifting a pail. Yes, the force was applied to the pail to be able to lift it up. Carrying a pail. No, the force and displacement are not in the same direction, just like number 3 that we had a couple slides ago. Picking up a dumbbell. Yes, force is done on the dumbbell because this is just like lifting up a pail. It moved in a force. Holding a dumbbell. No, because the dumbbell does not move. Reading a book. No, there's no force, no displacement, and unfortunately, no force applied, no distance or displacement either. Okay, so work. We're going to go back through the equation and then try some practice problems calculating work and other parts of it. So remember that is W is equal to F times D. Joules is equal to Newton times a meter. All right, first one. Brett's backpack weighs 30 newtons. How much work is done on the backpack when he lifts it 1.5 meters from the floor to his back? All right, I want you guys to pause the video, use the equation on the last slide to calculate the work done. Press play when you're ready for the answer. All right, so first thing you did was identify what our given variables were. So we have force, 30 newtons, distance, 1.5 meters, solving for work. Here's our equation. Simply multiply the force by the distance. We get 45 joules. Okay, and when you write work, make sure that you do write a joule instead of a newton times a meter. All right. Next one. What is the work done on a car that is pushed with a horizontal force of 4,000 newtons, a distance of 30 meters across the road? Again, pause the video, try this one out, and don't forget to show all those units. All right, let's see how you guys did. So again, we are solving for work. We have a force of 4,000, distance of 30 meters. We multiply the force and the distance. There we go. 120,000 joules of work. So breaking down the units, Newton times a meter, which a Newton is a kilogram times meter over second squared. So acceleration times mass, and then times distance is a joule. There we go. All right. Now, I'm going to give you guys a little bit more challenging problems. You are not going to be solving for work. You're going to be solving for other parts of it. But again, try pausing the video and press play when you're ready for the answer and the explanation. All right, first thing to do to solve this problem is pick out what we know. So there is a force of 25 newtons, and the amount of work being done is 50 joules, and we want to know how far she lifted the grocery bag. So we're looking for her displacement. All right, so I am going to actually first rewrite 50 joules to 50 newton meters, because a newton times a meter is a joule. And if I know that displacement must be in meters, all I need to do is take my newton meter and divide it by a newton to get a meter. That's exactly what I'm going to do. So 50 newton meters, or 50 joules, divided by 25 newtons. We get newtons to cancel out, and we have 2 meters for our. What? What? Okay. All right, that was weird. Okay, so we saw the end of that. I will try to crop this out. All right. Hey everyone. Sorry if that got a little chopped at the end. We had a little malfunction. All right, but it was 2 meters for the final answer. All right, let's try this one out. The baseball player does 1,234 joules of work when hitting a baseball into left field. Assuming the baseball landed 100 meters away from home plate, how much force did the player use to hit the ball? All right, again, try pausing the video. When you are ready for the answer and explanation, press play. All right, first thing to do to solve this problem for her displacement. Okay, solving this one. Okay, so we have first our work is 120 or 1, 2, 3, 4 joules, and it was hit a distance displacement of 100 meters, and we want to know the force, and that will be in newtons, of course. So I'm actually going to do the same thing as I did last time and go 1, 2, 3, 4 newton meters, and think about it in the same way as I did last time. So if I have a newton meter and I want a newton, I divide it by a meter. That's exactly what I'm going to do. 1, 2, 3, 4 newton meters or joules divided by 100 meters. Get the meters to cancel out. And we are left with 2.34 newtons. All right. There you go. Okay. All right. Thank you guys for watching. This last slide is just a reflection, and please let me know if you have any questions.